Hello kidlings and welcome. Algebra 3-4 again, Chapter 3 video study guide with example problems. Now these example problems actually come from your Chapter 3 review homework that you have assigned Friday. Okay, and there will be two other problems that I'm going to do. They're numbers 7 and number 8. There'll be two word problems doing systems of three equations. In another set of notes that we had. So those will be extended at the end. You get two more sets of word problems, and we're on our way. I'll just go ahead and get started now, and yeah, enjoy. Okay, we're going to start off with the system of equations. Now this is what this whole chapter is about, system of equations. Let's read off this definition here that I have. It's a collection of two or more equations with the same set of unknowns. Now, unknowns we refer to as x, y, z, whatever, any sort of variables that you have. They are the ones that can change. We don't know the answers to them, and when you see a system, you'll kind of know what I mean. Whatever I have for x in one equation, I have in another equation, same with y and z. Now, we've been referring to only linear systems so far, no x squareds or anything. Now, in a linear system of equations, there are three unique types of solution sets. Okay? One is called independent. And an independent, that means you have two different lines here. Let's say I draw a line right there, and then I draw another line over here in orange, and it crosses, say, right there. These two different lines, you notice, as we've done with equations in the past here, they have different slopes. And they don't have to have a different y-intercept, but in this case you'll see they have a different y-intercept. But different slope means they will intersect. It means they are not parallel. Okay, so if they're not parallel, they'll have, like I said, some point of intersection. In this case, it's at -1, 0. That is your solution. If I point to that right there, -1, 0, that's my x and my y value that makes these two equations true. Now, I don't know these exact equations. I just drew these lines. Looks like this one has about a slope of up 3 over 4. This one has a slope of about down 2 over 4. So about down 2 over 1, or down 1 over 2. Etc. Different slopes, different y-intercepts. You find those lines, you plug this into both equations, and it turns out that because this point is a solution to both equations, this point is a solution to this set. This is called independent. Something that's more of something to memorize, I suppose, than actually get a huge delving into what that word means with respect to this, but that's an independent system, it has only one solution. A dependent one has an infinite number of solutions, and it'll go simply like this. Let's say I have this blue line here. Copy and paste, and bring it on over. Okay, this line crosses through right there, sure. If I make another one. I'm going to make it green. This will be the same line. I'm going to make it actually, in fact, I'll make it a little thinner so you can see both of them together. There's green and there's blue together. Okay, now they are the exact same line, which means all of these points, this point here, and here, and here, and all the way up, whatever xy value I'm referring to, doesn't matter. All of these obviously work for the blue line. They also work for the green line because they're the exact same line. That gives you an infinite number of solutions. That doesn't mean it's all real numbers, because obviously you take this point out here, it doesn't work. But there's more than one solution. I can choose as many as I'd like along this line. So for instance, this point right here, 1, 2, 3, 4, 5, 6, 5, for example, is a solution to both these equations because they're both the same equation. Now, when you see these, you don't see them as both y equals mx plus b form and written the same. One might be a multiplier of the other, but you put them in slope-intercept form, they'll both be the same. Inconsistent, let's go ahead and paste these guys in again. Here's one, crossing at our infamous -1, 0 spot. And I'll make another one. Let's make it green again. Okay. These will never intersect. They are parallel lines, and they run on forever, but they never cross. Now, this blue line has a certain number of has an infinite set of solutions up here, just like I talked about before. The green one does as well. But in these lines, you will never get the same solutions. This xy value right here, 4, 1, is not a solution to this blue line. So you're looking at something where they have no solutions. Yes, there's a solution individually and individually, but for a system, they never ever intersect. Again, in this example here, the independent solution, they intersect once. Here they intersect an infinite number of times. And by the way, let me write this up here. They have same slope and same y-intercept because they are the same line. In this case, they have same slope, but to be different lines, they must have a different y-intercept. And if you take a look at this example here, this y-intercept's between 0 and 1. This one is about -2. So different y-intercept, they have to be different lines. And that's called inconsistent. So it's independent, one solution, dependent, infinite number, and inconsistent, no solutions. So let's do three examples here. We're going to determine if each system of inequalities is inconsistent, independent, or dependent. This is actually equalities. These are all equations. So ignore that. These are all equations. Equal sign says that. What I'm going to do, and this is actually my preferred method, is I'm just going to put these all into y equals mx plus b form. The main reason why I do that is because, well, I'm familiar with graphing these this way. Now, I won't actually graph these. But if you take a look at graphs, you can tell what will happen, and I know how to graph them that way. But I also know, take a look at this equation, what my slope is and what my y-intercept is. So I divide by -3, I get y equals 1/3 x minus 1/3. Okay, now that's for this blue one right here. The reason why I'm doing this is because these are unique. By looking at the graphs, they're unique by saying, if I know what my slope is and they're different, then I absolutely know these will intersect only once. Therefore, these are independent. If they're the same slope, now I just have to figure out, do they have a different y-intercept or the same? Because then I know they're either the same line or they're different parallel lines. So that's my objective. I'm going to go ahead and do that with this one right here. And the reason why I'm not doing it in standard form is because standard form doesn't give you slope or y-intercept. So I'm going to add 2x, and I get 6y equals 2x plus 5. Divide by 6, I get y equals 1/3 x plus 5/6. All right, and now I analyze both of these guys right here. I have y equals 1/3 x minus 1/3 and y equals 1/3 x plus 5/6. I'm looking at same slope, and the y-intercepts are actually different. So what you're looking at are parallel lines. They will never intersect. They cross at different paths. And yeah, same slope, so they won't ever intersect. So here, this would be considered inconsistent. No solutions, and we'll talk about times when they have no solutions if we run across an equation like that. No solutions, and it's inconsistent as a result. Okay, next one, I'll be doing the exact same thing. No difference here. They're in standard form. Let's get them slope-intercept form. This equation, 4y equals -x plus 2. Y equals -1/4 x plus 1/2. Okay, so there's one equation in blue. And in green, I'll bring this one over. -y equals -2x plus 1. Divide by -1, multiply by -1, y equals 2x minus 1. So there's another equation, and you can tell right here, completely different kinds of lines here. I'm looking at one that has a slope of -1/4, one that has a slope of 2. It doesn't matter if the y-intercepts are the same or not. The fact is these will only intersect at one point. Different slopes, one point of intersection. So that means one solution. And if you remember, one solution means an independent system. Okay. And finally, one more right here. Use my blue. First equation. Subtract 2x. And then divide by 3, y equals -2/3 x plus 1/3. Kind of close to that other equation over there. And let's go and use green for this one. 6y equals -4x plus 2. And y equals -4/6 is -2/3. And 2/6 is 1/3. Okay, now you're taking a look at y equals -2/3 x plus 1/3, y equals -2/3 x plus 1/3. Hey, they are the same equation. So if you graph them, it's the exact same line. That's an infinite number of solutions. And that is a dependent system. Sorry for the kind of lousy handwriting on this as I do this on this program. Not the best. So any questions with that, you may ask away as you see those. But hopefully those equations make sense. Oh, by the way, I didn't really mention this. I am jumping out of order. This is number 6 on your review sheet. I'm doing this first because this is kind of the first thing that applies when you're doing your notes. So hopefully that kind of makes sense. You know, I'm going to jump to all the other ones as I do them. Doing more notes here, let's talk about solving a system of equations. So before we kind of just, you know, found out what kind of system it'd be, how many solutions we expect. Now we're going to find out what x and y really are. So solving a system of equations means finding the ordered set that satisfy each equation. When you have a system with 2 equations and 2 unknowns, you're just looking at an x-y set, coordinate pair. What system or set of values work? If there are 3, which we'll get into later, maybe x, y, z, you'll get an ordered triple instead of an ordered pair, etc. Okay, there are 3 distinct methods which to solve a system. First one I'm going to talk about here, the one that's highlighted, is graphing. Now we kind of did this by me graphing before. What we're going to do is we will graph and we will find where they intersect, if they do at all. So this also applies for inequalities, which I'll kind of star because actually it's kind of interesting. The problems that you have on your sheet are all inequalities. So that'll be kind of important. But I'll talk about an example if they are equations as well. You want to graph your equations on the same axis. So like you saw before, if there are 2 equations, graph them both together. And find which points satisfy all equations in the system. If there are any. Again, parallel lines means none. For equations, for inequalities, you're looking for the shaded regions. And we've talked about inequalities ad nauseum. And what you do is inequalities, I'm just going to draw a line and shade right here. The shaded region is the set of points for which makes the inequality true. So I want you to make sure that that is making a lot of sense there. It's not just shading, it's every point that satisfies the equation. So let's go ahead and solve by graphing. Graph, clearly show the solutions for each. Okay. What's going to be important for me when I graph is I need to put it in slope-intercept form. This one clearly is, this one is not. So let's rewrite it right now as we go along. This will be negative 2y is greater than negative 3x plus 6. And when I divide by negative 2, my inequality flips. You remember that from the previous chapter. Y is less than 3 halves x minus 3. So here's one inequality, and here's the other, and I'll graph both. I'll first graph them assuming they're lines only, and then we'll talk about what happens when they're inequalities. So my first one here, let's go ahead and make it blue. That'll be this guy right here. Start at negative 5, okay, and we will go, hang on, negative 5, and we'll go down, oh no, see, up 2 over 3, like so, okay, and down 2 over 3 this way. And so your graph kind of looks a little bit like that, and I'll make it a little bit taller. Now, because it's an inequality, you have to notice whether it's going to be dashed or solid. This one will be solid because it's also equal to. I'll do that a little bit in a second there. Your other one, let's make red. Let's make red will be starting at negative 3, and I'll go up 3 over 2, like so. Okay, and down 3 over 2, like so. Okay, whoops. And when I graph this, probably looks a little bit like that. When I graph this, it'll be going down a little bit like that. I'm going to line them up a little more. Okay, there we go. Oh, by the way, this should be dashed line. Okay, dashed line, indicating it's not equal to. Now let's say these were both equal to. Let's say this said y equals and y equals. When you solve, and this is not a perfect example, this is actually a poor example for a few reasons. When you solve, you want to find out where these intersect, and these intersect right here. Notice they did not intersect right there where that other red dot is, and that's something that you got to be very careful of. When you graph, you got to be exact. You have to exactly know where they intersect, and this is why it's a bad example, because this doesn't land on an integer. You can see these blue dots represent exactly on integers. Anything in between is not right on an integer. So this lands at some point. It's about negative 2. Okay, so let's say it was this point. That would be negative 2, negative 6. And that would be your point where you solve, meaning if you plug in -2 and -6, it satisfies both equations. Now, this is not true for this case, and these aren't equations anyway, so let's go back and talk about shading. Okay, when I shade the red, and I don't really know how to make it lighter, but when I shade the red, I have to do y is less than, so I'm going to shade underneath for this guy right here. It's going to look like that, and also underneath right here as well. It never stops shading. Everything underneath my threshold, that is the dashed line. The blue is y is greater than or equal to. So when I shade blue, I'm going to shade above it, like so. And to keep this line here, I'm going to shade right there as well. And you kind of see that there. Now that includes all this. I'm not going over it, and same with the red. Your answer to this thing is the intersection for which everything is shaded in both regions. I'm sorry, for both inequalities. Plus, perhaps, if these lines intersected and they were both solid. Now, they're not both solid. This one's dotted, so that intersection point is not a solution to this. But everything inside here, follow my cursor, everything inside here is a solution for both inequalities. So I'm going to go ahead and delete the other stuff that I started to shade. In fact, I got to shade that blue again, it looks like. I'll go ahead and shade that again. Okay, and I'm going to delete this red right here. Okay, redraw the red a little bit more to emphasize that that's all true. Let's go ahead and look down here, and I'm not going to do this for every equation. I'll just do it for this one. I got y is greater than or equal to 2/3 x minus 5, and y is less than 3/2 x minus 3. Okay. Again, what this means is I pick a point. That's a 5, by the way. I pick a point somewhere in here. Let's choose the point 2, 3, 4, 0, right there. Okay. If I plug in 4, 0 into both inequalities, this is important, it must be both. If I plug it into both inequalities, both items will be true. Now, that's actually a bad example because I don't want to do 4/3. But, take a look. Is 0 greater than or equal to, that'll be 8/3, really. 8/3 x minus 5. Well, 8/3 is a little, it's less than 3, so it's about -2 here. Is 0 greater than or equal to -2? Of course. 0 here, is it less than, that's 12/2, which is 6. 6 minus 3 is 0 less than 3, of course. So both of these are true. And yes, all of these within here will be true when you plug them in. If I try a point like 0, 0, that will not be true for the red, because remember, red I shaded underneath, but it would be true for the blue. Try that. Your red is the bottom one. Is 0 less, let's see, red was the 3/2 x minus 3. So this will not be true for red, right? 0 is less than -3, not true. 0 is greater than or equal to -5, that is true. But we need it for both of them, so it's going to be within the shaded region there. And I'll move on. I'll go more quickly for these other ones, but you have to know how absolute values work and how we graph them. So let's go and do that. This one is in proper vertex form for absolute value. I'll make sure to do this one blue again, and I'll do this one red as I do it. Want to put it in slope-intercept form, though. So it'll be y is greater than 1/2 x minus 3. So let's go and do the absolute value one first. My slope, my stretch factor here is 1. My vertex is at 3, 4. If you remember that. Won't take time talking about it. Something to practice. If you'd like to know more about them, please watch my other video that you watched possibly for Chapter 2. The Chapter 2 review video. This is going to look like that. It's going to go V-shape and upward here. Not much room to work with, but that's not important. What's important is I'm shading underneath this guy. And this will be, by the way, a dotted line. Let's do blue. Dashed line. So, that is solid. A dashed line would look like that, going through, that going through, and then I'd shade underneath. I'm not going to shade underneath yet because it gets a little messy. I want to figure out where this one goes. This one here, y is greater than 1/2 x minus 3. Negative 1, no, it's positive. 1/2 x minus 3, like so. This time, actually, when I shade, I'm actually just going to shade the region in between that I know to be true. Okay, so here, this will also be a dashed line. I'm going to make it red. Okay, it's going to go through like that. Okay, in my shading here, I'll make red plus blue equals purple. Let's make that purple as we shade. This one was less than, so for blue I'm going to shade below, and red I'm going to shade above. So as you can tell here, my intersecting region will be everything that's less than blue and greater than red. So my shaded region is all right here, and that's all I'm concerned about. Everything that fits within here. Obviously, blue extends forever down here. Red extends forever up here as well. But my shaded region that I'm concerned about is right here, and this is my solution set. It's all of these points. If I plug in any set of points right here, any point, it'll work for both inequalities, and that's what's important. Okay, moving on. Both in vertex form already, which is great. My first one I'm looking at, red versus blue. First one I'm looking at is vertex of -2, 4. So I'll start at -2, 4, and I will go, this is down 1 over 1 continuously. Down 1 over 1, down 1 over 1, yada yada. This is less than without the equal to, so it'll be a dashed line. Okay, continuing on that slope and on that path, about like that. And like that. And I would shade underneath. Again, I'm not going to do that yet. This guy right here has a slope of 1/6 up here. 1, 2, 3, 4, 5, 6. And it looks like it goes up 2 over 1, so I don't get much room with this guy. Now y is greater than or equal to, so this will be a solid line that is blue. Okay. So it would go forever like that, and forever like that. And I would shade above. Now this one's interesting. Actually, I will decide to shade these. I would shade above here, and I would shade below here. Now the question is, what's my solution set? Because if you remember, I have to have these sets intersect. There is no point which these intersect. I plug in a point up here, it'll satisfy this equation, this inequality, but it would not satisfy this one. I plug in a point here, it would satisfy this inequality, but not this one. I plug in something here, it would satisfy neither. So I don't have a solution set which satisfies any equations, and that's important. This one has no solution, and that's important to write. In the other ones, there's an infinite set of solutions, and it's hard to actually write what they all are. This one has no solutions. No solution, no solutions either way. Okay, that was for graphing. So let's check that one off. We're done. Let's look at substitution. We've done substitution before. You can plug in a value for x or something like that, and then you solve for whatever. This one's going to be a little different because now you have multiple variables. So what we're first going to do is choose a variable for which to isolate in an equation. That means get it by itself. We've done that a lot. But you're going to get something by itself, and you might have another variable on the other side of that equation, which is going to be fine because what we'll do is substitute the information. So let's say you had like x equals something y, whatever. You'll use that something y to plug in for x. You'll plug it into another equation till you have one unknown variable. What I mean by that is we start with 2 equations and 2 unknowns. You can't solve either equation by itself. So you're going to create an equation where there's only one unknown variable. You're going to solve for that variable and then trickle up. What that means is go up through your work and substitute in that value that you found for one of your variables to solve for your other variables, potentially. So let's go and take a look. I'm actually going to look back at elimination after this. Let's take a look at this one. No, I don't want to do substitution with that one. I'm actually going to do substitution right here because it's possible for me. Probably not most advised. You have some fractions here. It's not my favorite to look at. In fact, you know what? Here, before I do this, I'm going to eliminate some fractions. I'm looking at number 2. I'm looking at part B. I'm going to multiply this by 4. I don't like this over 4 fraction. I'm going to multiply this guy by 7 here. I don't like that over 7 fraction. So let's change this. It doesn't look good to me, right? All right, so when I multiply this by 4, I'll get x plus 4y equals 36. When I multiply this guy by 7, I'll get 7x plus 7 equals 3y plus 42. Fraction's gone. I feel better. I don't feel as good as I can. For substitution, it'll be okay, but I'm going to continue on. I like putting these in standard form first, and you'll see me do that a lot as we go through this. So I'm actually going to subtract 3y and subtract 7 in my bottom equation. My variables will line up, and you'll see that, there's some nice benefit to it. There's some good charms to it, especially when you do elimination. In this case, we won't be doing elimination, but in substitution, let's talk about that. I'm going to look at this x here. Reason why is because I don't have to divide by any numbers. I feel like it'll be easy to solve. All I have to do is subtract 4y. In fact, let's go ahead and do that. X equals negative 4y plus 36. And the benefit that I have of this, although I'll get big numbers, I do understand that, and I might have to go to the calculator, is I need to solve for one of my variables. Now you can tell, if I solve for x in this one, or y in this one, or this one, it'll have the other variable lurking on the other side. I didn't solve for it. So what I'll do instead is take negative 4y plus 36, substitute it in right there for x. Because when I do, I will have an equation that has only y in it. And as we know in algebra, that is possible to solve. So this is 7 times negative 4y plus 36, again, big number, minus 3y equals 35. So I get negative 28y plus, that's 252, yeah. Minus 3y equals 35. Work on some subtraction here, and again, if I need to find a calculator, I'll go ahead and find that. That should give you negative, I don't want to be wrong here, 217, and I'm going on a whim here. You divide by negative 31, that should give you 7. Okay, so y equals 7. Now, there were probably easier ways to do that. A lot of people prefer substitution. You'll kind of see how that works. But y equals 7. Okay, I found one of my values. I didn't find x yet, though, and I'm not done. Okay, so plug in. Here's what's going to happen now. I'm going to substitute 7 in for y. You can do it in any equation. I can plug it into here, here, or here. My preferred equation is this one right here because I need to solve for x. I'm already saying x equals this. I might as well work with what I have here. So if y equals 7, let's go and rewrite negative 4y plus 36. So x equals negative 4 times 7 plus 36, which is negative 28 plus 36, which is 8. So x equals 8. If I wanted to write my solution as an ordered pair, it's 8, 7. And if you remember, what this means is the coordinate point 8, 7 on a graph is the point for which these two lines intersect if you graphed them. So if I put these in slope-intercept form and I decided to graph, these would intersect at this one point, in this one point only. This is an independent system. They have different slopes apparently, and that's what you do. So that's the idea behind substitution. You want to solve for one variable. This one was simple enough because this was 1x. Didn't have to divide by anything. Substitute it into the other equation. Again, if you're looking at your notes here. Substitute information to other equation until you have one unknown variable. In this case, we broke it down. We only had y left. We solve for y. And then we insert that back into another equation to solve for the other variable. So you're looking at that information trickle up, meaning go back up into your equations there, figure out what your other values are, and make it happen. Okay, I'll do substitution as I see fit the rest of the way, but I want to introduce elimination and make sure you understand that one. Okay, I'm going to actually expand on elimination just a little bit first, before I do a problem with it and talk about this. I want you to understand what elimination is. Not eliminating methods. We know what additive inverses are, hopefully, how we can make 0, but what we are doing when we add equations. Okay, I'll give you a simple example here. X minus 4 equals 2. We want to solve for x. What we do, well, first of all, in terms of math, we say we subtract 4 from a number, we get 2. What's that number? We get 6. Why? Because we add 4 to 2 to figure out what that number is. So we add 4. But we don't just add 4 here. This isn't x minus 4 equals 6. No. This is x equals 6. So how did we get x on this side? Well, we happen to have to add the same thing on both sides of the equation to make that true. Additive inverses eliminate the 4, and we get x equals 6. The important thing about this, though, is that whatever you do to one side of an equation, look, we actually changed what was represented on these sides. This is like saying 2 equals 2, because if x was 6, that'd be 2 equals 2. And then we added 4 to both sides to get 6 equals 6. We maintained what's called balance. And I'm going to talk about balanced values a little bit here. You have to add the same thing to both sides to make this true. And that's fine for any equation. As long as you add the same thing to both sides, there is zero harm. So let me go back to saying that when I do an example to see if that makes sense as I do that. Okay? As long as again, I'll say it one more time, as long as I add the same thing to both sides. You understand that here because you both see them as 4. But you're going to see these things as different values when I do elimination. And again, as long as I add the same thing to both sides, there is zero harm. Okay, let's talk about elimination. We're going to pair up equations so like terms will be combined when adding. Again, balanced values. I'll talk about that later. Pair up equations. What I mean by that is, remember in this equation I made these in standard form? Get standard form out because you want to add x's together and y's and constants. Next thing, we're going to choose a variable for which to eliminate in our system by finding additive inverses. When I do an example, you might not have something that are already additive inverses, like here, 4 and -4. So you're going to create that by multiplying by certain numbers sometimes. We'll continue this until we solve for a variable. So we will keep eliminating variables till we have one variable. Just like in the substitution method, we got to only y to solve for y. We're going to do the same thing if we want to solve for y or x. We'll go back and trickle up. And after you do elimination once, you don't have to keep eliminating. You can choose to substitute again after that. That's fine. You don't have to keep eliminating. So I'm going back to number 2 here. And I'm going to play elimination. Now this is not, again, this is kind of more difficult. You have to figure out what to eliminate here. I'm going to go ahead here and use a little bit smaller numbers. I'm going to eliminate y and solve for x. Now what I have to do is add these two values together so that I get 0. Now I talk about adding. We just talked about this before, this whole x minus 4 stuff. I have to add the same thing on both sides whenever I add. I want you to take a look here at this equal sign. This equal sign means that this side equals this side. So before I actually do any elimination here, I want you to take a look at what happens if I add. I'm going to add 7x minus 2y to the left side. And I'm going to add 28 to the right side. Little do we know, this is actually the same thing. 28 is equal to 7x minus 2y. Technically, I'm kind of adding 28 on this side. I just don't want to because I want to combine like terms here. I want to add 3x and 7x and get 10x. I want to add 5y and negative 2y to get 3y. And here on this side, I want to add constants and I'll get -1. Now, does this equation help me? No, actually it doesn't help me at all. But the fact is, this is yet another equation that would work with this system here. This is the addition of these two equations. And I could add, because I added the same thing on both sides, 28 and 7x minus 2y are the same thing. That's something that I just wanted to make sure that's super important. That is why we add when we do elimination method. And that's why I talked about that before. Okay, so what I'm going to do here is I said, hey, I want to eliminate y. Now, 5y minus 2y doesn't give me 0, so I can't eliminate it doing that. But what I'm going to do is multiply this by 2, because I want to find a least common multiple of 5 and 2. In this case, I'll get 6x plus 10y equals -58. Make sure to multiply by that one as well. On the bottom here, that I'm going to do in red, I'm going to multiply by 5, for the very reason that I want to get -10, the additive inverse, there when I multiply by 5 on my bottom equation. So I'll get 35x minus 10y equals 140. Big numbers, but looks like some things will eliminate pretty well. Now I can add again for the same reason that 35x minus 10y is the same thing as 140. So I'm going to add technically 140 to both sides. Just I want to combine like terms here. So 6x plus 35x is 41x. 10y minus 10y is 0. That was the whole purpose of this. I wanted to get rid of my y values. 140 minus 58, I believe I get -82. Okay, divide both sides by 41. Good number again. X equals -2. I wanted to go for that. All right, I'm in business. I found my x value. Let's go ahead and find y. I can plug in -2 into this equation, this equation, this equation, or this equation. When in doubt, choose smaller numbers. or less negative numbers or whatever else, I'll go ahead and use the first equation here. Now notice, I'm not going back and doing elimination method again. I can and choose to eliminate x and solve for y, but I think that'll be more work in the end. I already have what one value is. Let's go and substitute it. So in substituting, I'll get 3 times negative 2 plus 5y equals negative 29. Negative 6 plus 5y equals negative 29. Add 5y equals... wait, is this a good number? I just want to make sure I didn't get any things wrong here. I want to make sure I get good numbers. So I'm going to add 6 and I get negative 23. So you'll notice, this is actually a good thing I didn't do elimination or whatever else. I'm going to get a fraction answer. Now I want to double check I got this right. I'm not sure I did. You know, we can screw up problems as well as teachers. 3 times negative 2. Okay. It was negative 58 and positive 140. Oh, I'm sorry. This is positive 82. That's why. Well, you see, got something wrong there. So I'm going to plug in positive 2. That would be positive 6. I subtract 6. I'll get negative 35. See, teachers get things wrong as well. And I'm okay to admit my mistake. Negative 35 over 5 is negative 7. So there we go. That was a positive 82. And I just tested my Algebra 1-2 students on this kind of stuff. Make sure you don't screw that stuff up. Okay, so my ordered pair there is 2, negative 7. And again, that means that when these lines intersect, they intersect at that point on a graph. Now you can double check your work. Again, make sure that you plug in 2 and negative 7 and see that it works in these equations. Plug in 2, negative 7, so you get negative 29. Plug in 2, negative 7, see that you get 28. It needs to work for both equations. Okay, this one is a fraction example. That's not so pretty. I don't like fractions. I do not want to use fractions. We got to multiply these. Before I multiply them by numbers to eliminate, I'll multiply by numbers here in part C to get rid of fractions. So here, I got to multiply by a number that is going to eliminate both the 4 and the 3. So you got to find a least common multiple of 4 and 3. In this case, 12 would be that number. So let's go and write that. 12 over 4 is 3. So this will be 3 times x plus y. 12 over 3 is 4. So this will be negative 4 times x minus y. That'll be equals 12. So a lot of work to be done on this one. Multiply this one by a common multiple of 2 and 4. In this case, 4. Right? I don't have to multiply by 8. I can do a smaller number. So multiply by 4. 4 over 2 is 2. So that'll be 2. Hang on a second. 2 times x minus y. Plus 4 over 4 is 1. So that's x plus y equals negative 36. And let's start distributing, combining like terms, all that good jazz. So let's go ahead. I'm going to get this one down here. That'll be 3x plus 3y minus 4x plus 4y equals 12. So that is, I'll write down here one more step. Negative x plus 7y equals 12. In this one right here, I'll distribute it. I get 2x minus 2y. Plus x plus y equals negative 36. Combine like terms, I'll get 3x, what do I have, negative y plus y, minus y equals negative 36. Okay, this is my official system right here. I did some work before I got this problem started. A little bit of work goes a long way here. And now I can choose, do I want to do elimination or substitution? A lot of people in this case do elimination. I'm okay with that, mostly because, now look, I can multiply the bottom by 7 to eliminate my y's, but I want to do, 7 times negative 36, not so fun. If I multiply the top by 3, I will eliminate my x's. And you're going to see something that's actually a little better. All right, so I'm just going to go ahead and write this down here. I'll get negative 3x plus 21y equals 36. Now I get to add, sorry for the whole mess, now I get to add these guys down below. Do that in green, new color. 3x minus x is 0. We anticipate that. That's why we're eliminating, or that's why we multiply to eliminate. We get 20y here equals, hey, look at that, that's 0. Kind of interesting. Divided by 20, y equals 0. Remember, 0 over 20 is 0. Okay, so y equals 0. Now I can use that and substitute 0 into any equation. I'll just do it in the first one here. If negative x, just in case you don't know how this works, negative x plus 0 is 12. If the opposite, if opposite of x is 12, then x is the opposite of 12, which is negative 12. So x is negative 12, and your solution set, therefore, is negative 12, 0, that one-ordered pair. All right? So we solved for all three of these guys. This was only two equations and two unknowns. We have a lot more to go here. Okay, systems of three equations. We did two equations. Now we're going to three. We haven't graphed before with three equations, or not three equations, with three unknowns. That is three-dimensional graphing. So we're just going to do elimination and substitution here. Let's talk about elimination first. And I'm going to choose one of these problems to do elimination. I'll just choose this one, I suppose. And substitution, I'll do the other. In elimination, we're going to pick two sets of two equations. Okay, meaning I'm going to decide and say, I want to pair up like this equation 1 and 2. I'll write these down. 1, 2, and 3. An equation 1 and 2, and equation 1 and 3, or equation 2 and 3, or whatever else. Because what I'm going to do is I'm going to do elimination on two different sets. Because I want to eliminate the same variable. When I do, I end up with my goal, which is to get a system of two equations and two unknowns, just two variables. Because then I can do as I normally solve. Okay, solve the system of two using either substitution or elimination. So after I do elimination in the first part, I can then use my preference. So I'm going to stick with elimination for one of them the whole way down, no matter how messy it gets. And I'm going to stick with substitution the whole way down to the other one to see how messy it gets, no matter how messy it gets as well. So again, taking a look at this. I look at my, you want to look at this carefully and say, there are easier variables to eliminate than others sometimes. In this case, I'd say x is the most difficult because I'd have to multiply this one by negative 3 to combine with that, or multiply this by negative to combine with that. Negatives get iffy. Y's are okay, but I'd have to multiply these guys by 2 to make it happen. Z is already set up for me in that if I add equations 1 and 2, negative z plus z, and if I add equations 2 and 3, negative z and z, I eliminate them immediately. So I'm going to use some mental math here to save myself some room. I'm going to add equations 1 and 2. So I'll get x plus x, which is 2x, y plus y, which is 2y, z, negative z plus z, which is 0, negative 1 plus 3, which is 2. 2x plus 2y equals 2. For the sake of easing this up already, I can divide everything by 2 in this equation. I get x plus y equals 1. This is one of my two equations in my system that I'm going to have, where basically I've eliminated z. Now I'm going to have nothing else but x and y to solve for one of these. Now let's add equations 2 and 3 together. So I'm going to add and get 4x minus y plus 0 right here equals negative 1. And that can't simplify anymore. I'm going to get 4x minus y equals negative 1. And voila, I have a system of two equations and two unknowns based on this system. Now you're going to do just like we did before. And you know what? Elimination is kind of set up for me again. I can add immediately right here, and I will eliminate y's. Remember, add both sides of the equation here. I'll get 5x plus 0 equals 0, 1 minus 1, divide by 5, x equals 0. So now what's going to happen here is I get x equals 0. I need to still solve for y and z. I need an ordered triple. I need to get all three of them. What better way to solve for y other than plug in 0 into one of these equations? How about this one right here? If x equals 0, then y equals 1. So there's my other one. That one actually worked out pretty well for me. It's not always that perfect. And the final one, I need to plug these two values into an equation where I have z. Let's do this kind of easy one right here. I have x plus y plus z equals 3. So 0 plus 1 plus z equals 3. 0 plus 1 is 1. Subtract 1, I get z equals 2. And that's actually kind of a fun ordered triple right there. I get 0, 1, 2 if I'm thinking about x, y, z. Plug those into all three equations to double check. Make sure you get those on the left side that you get on the right side, and you're set. So that one's elimination, and I'll be doing a lot more of it because I'll be doing 5-word problems. So you're sticking with me for a long time if you're watching this entire thing. Anyway, that's my solution. And this is a point in space. We haven't done three-dimensional graphing, but this is it'll be interesting when you do it just to see exactly what it looks like and what it means when you intersect all these guys together. Okay, the next one I'm going to do substitution with. And when I do substitution, here's how it looks. It's the same thing as before. I'm going to isolate a variable. I'm going to choose one equation to solve for one of its variables. So I'll choose one to solve for. And if you remember last time, I chose one that only had one coefficient with it, so I'm already eyeballing this y, and kind of this z, even though it's a negative z. So I'm going to look at one of those to isolate and solve for it. I'm going to substitute that solution that I have for that into my other two equations. Obviously, if I sub into the same equation, let's say I solve for this y, which will be my preferred thing this time. If I solve for this y, in terms of x and z, I'm substituting it back into this equation will just get me the same thing on both sides, like -3 equals -3. That doesn't help me. I need to get something where I'm getting differing systems. I need to get two equations and two unknowns. So what I'm going to do here, again, looking back at substitution, my goal is to get to a system of two equations with two unknowns, solve the system using either substitution or elimination, and as I told you by the end, I'm going to still use substitution no matter how messy it gets. I know I'm sticking through it. Let's see how we do. I want to solve for this y, which means subtract 3x and add 4z. So I get y equals -3x plus 4z minus 3. Now this gets a little fun because you do a lot of distribution and combining like terms. Now what I'm going to do is take this solution for y and substitute it into this y here in this equation and this y into this equation. Again, I'm plugging them into the equations that I haven't yet plugged them into, that I haven't yet used. So taking this equation, I'll get 5x plus all this, nothing to distribute really, just -3x plus 4z minus 3. I believe this was a minus z. Actually, let's check. That is a minus z equals -6. Let's just combine this now and figure out what we get down here. 5x minus 3x is 2x. 4z minus z is 3z. And if I add 3 to this side, I'll get -3. So one of my equations in my system is 2x plus 3z equals -3. In my second equation, I have to substitute this in for here, y, and distribute the 4. So I'm going to get 10x plus, and I don't want to spend too much time. Well, let's go and do that. 4 times the -3x plus 4z minus 3 plus 5z equals 15. Let's use a different color so I'm not too spatially inadequate. Get 10x plus, minus. This will be minus 12x plus 16z minus 12 plus 5z equals 15. When I combine like terms here, get 10x minus 12x, which is -2x. And look, elimination would be so perfect. I hope I don't regret what I said about do this at all costs. Plus 21z, oh, I'm going to regret this. You know what, we'll just do elimination. I'm sorry. I don't want to waste your time. That's really it. Equals. Now I'm going to add 12 over here, and I'm going to get 27. Okay? I've created a system, two equations and two unknowns. I've eliminated y just by substituting values in for y. Okay? I have my system. I am going to use elimination. I really should have used substitution on that side. I'm sorry, but we've practiced substitution. I hope it was enough. When I add straight down, I'll get 24z equals 24. You can see why sometimes some items are better than others. I'll get z equals 1. See, this is why I wanted to do substitution, so I could help you. But notice, if I divided by 2, I have a fraction. If I divide by 2 here, I have a fraction. Same with 3 and 21. I don't want to work with fractions and waste your day. I got z here. Here's the benefit of substitution, though. Let's say I did solve for x. I got x equals blah, 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 something in terms of z. Like z plus 3. Let's say it was that. I can trickle up mentally. I just plug in 1 for z, and I'm good to go, and I get x. And then, because you already solved for y, which we're about to do, you just plug in those values for x and z. So that's why if you can do substitution the whole way, it works pretty well. I mean, you can do it, and it's going to be very nice. But I don't, so let's move on. Plug in 1 for z in one of these equations. Let's, when in doubt, do the smaller equation. I'll get 2x plus 3 times 1 equals -3. So 2x, subtract 3, I get -6, and x is -3. Okay. So -3 and -1, keep those numbers in mind. I'm going to do this last part mentally. Again, substitution, you can do that. So y equals -3 times, remember x was -3, so that's going to be 9, plus 4 times 1. So 9 plus 4 is 13. 13 minus 3 Wait, is that right? 13. 13 minus 3 is 10. So I'm going to get y equals 10. So my ordered triple here will be negative 3, comma 10, comma 1. Ba-boom. You plug in those values into all your three original equations. That should work. I anticipate, because I didn't get fractions, that I did this problem correctly. You can do this any method preferred, but if you're looking at this, maybe this is a way you want to try it, just to get substitution in the mix. So we practice solving elimination and substitution. I'm actually going to do it 5 more times, because I'm going to do 5 more word problems with you. So I'm moving on. Word problems. Like linear models, it's important to understand what the question is asking. So you're going to look at 5 word problems here. 1, 2, 3, 4, 5. The question is always at the end, or so it seems. Or so, like this. Find the measure of each angle. I need to know what the measures of the angles are. I don't know that. Find the numbers. Obviously, these aren't questions, but find the angle measures. Blah, blah, blah. What is the measure of each of the angles? What was the average temperature in each of the 3 months? I actually like this word problem the most because it's kind of more real life stuff. But you look at those questions and you identify, these are the things that we don't know. If we don't know, these are the things that are called unknowns. Don't know, they are our unknowns. These are the things that we have as our variables. Label these variables. I want to define them as something and say, okay, they tell us information in the clue. They say, blah, 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 and we use those variables to create equations. Make sure that when you label variables, indicate units of measurement. I talked about that more in Chapter 2, so I'm going to avoid talking about that as much. I actually want to solve these problems for you, save you time. We'll talk about matching values with expressions. My recommendation, when you start writing these out, you want to write them out based on what the equation, or based on what the words say, what the sentence says. But after that, line them up. Remember, line up your x's, your y's, and your z's. If you don't have them lined up, you're going to have some issues there. It's good to know what you have and to know what you're missing. I'll explain why when we do some of these equations. Okay, problem number 1. 2 angles are supplementary. Oh, the other thing about word problems is it's important to know what they're asking. You have to know what supplementary means to do this thing. Otherwise, it's impossible to solve. What that means is angles add to 180 degrees. Now, you have 2 angles here, so 2 of them are supplementary. The measure of the larger angle is 60 more than 3 times the measure of the smaller angle. Find the measure of each angle. So this is kind of interesting. The measure of each angle looks like we're only referring to 2 angles, which means we only need 2 variables. That doesn't mean we don't need 3 equations. So here I'm going to call them x and y, angle number 1, angle number 2. But because they're talking about larger and smaller, and because I don't want to accidentally use x as the larger than as the smaller, I want to define x as smaller angle or larger, but I'm going to use x as a smaller angle. My units of measurement will be degrees. That's the degree symbol. And why I'm calling my larger angle the unit is also in degrees. Because when you create equations, you want, for instance here, if these are supplementary, that means x plus y equals 180. That is to say, degrees plus degrees equals degrees. That must add up with those units in mind. Okay, the measure of the larger angle, the y. I'm going to write this off to the side because I want this to be my clean system. The y is 60 more than 3 times the measure of the smaller angle. What you want to be careful of, a lot of people will say y is 60 more, so you're going to say y plus 60, and then 3 times the smaller angle. Here's the problem. If I add 60 to y to match 3 times this, even if this was just x, if I add y to 60, y is smaller then. I had to add 60 to get here, so this is actually backwards. Let me rewrite this again with 60 on the other side plus 60. Y equals 3x plus 60. What this means now, if y is my larger angle, it says 3 times the measure of the smaller angle. So I have to triple this. I have to add 60 to this amount to match y. That makes sense. If y is 60 more, then I have to add 60 to this one to equal that. So a lot of you guys are going to get this backwards. In fact, whenever I taught this, we did get it backwards. A lot. So, you just got to be careful with it. What I'm going to do now is I'm going to subtract y and add 60. So I'll get 3x minus y equals 60. No, I'm sorry, subtract 60. Subtract y and subtract 60, so that's negative 60. So my next equation here in my system, why I want to line them up? Well, it'll be very important. Minus y equals negative 60. I'll use whatever method. A lot of these times you'll see that I'll be using elimination. Not much substitution practice, unless it sets me up for it immediately off the bat. My final one, you know what? This isn't even a system of 3 equations. This one's a system of 2. So I really should have done these and set these up before doing systems of 3 equations. I didn't realize we were just running into 2. I'm sorry. But in doing so, okay, we've set up our system here. I'm going to use elimination. I'm going to add straight down because that'll eliminate my y values. I got 4x equals 120 and x equals 30. You know what? Yeah, I mean, you should be okay with the fact that I'm going back to some stuff and I'm staying consistent with word problems. I actually think this is just fine. I just apologize for saying we're going to make 3 equations because we obviously didn't. Okay, plug in 30 for x. I'll do it in this one. When in doubt, use smaller ones. 30 plus y equals 180. Subtract, we'll get y equals 150. And that makes sense. 150 plus 30 is 180. And y is the larger angle. And make sure that works in that one as well. You'll be set to go. Okay, word problem number 4. The sum of 3 numbers is 6. Ooh, we know we're using 3 numbers now. Looks like we got x, y, z. Find the numbers. These are numbers that we don't know. I'm going to already call them x, y, and z when I start defining these. Now, I don't know what to define them as. I don't want to call them just first number, second number, third number. Because normally they say, I'm sorry, they don't say that. Normally they'll say smaller number, middle number, bigger number. So I'll just call this number 1, literally, and number 2, and number 3. The units for these, well, you know what? The units are just units. Now, the number is not 1. This is just the first number. Number 1, number 2, number 3. So I have to make sure that when they talk about the first 2 numbers, we're talking about x and y. So when you create these equations, be very careful. Make sure you do that. All right, the sum of 3 numbers is 6. X plus y plus z equals 6. Make no assumption that these numbers can't be negative and that these numbers can't be the same thing. Okay, so don't just take a guess, go, oh, obviously it's 1 plus 2 plus 3. No, we have no idea. That's why we can't solve this yet. We need more information. The difference of the first 2 numbers, I'm going to write this on the side here. Difference is x minus y. Plus the third number equals 2. So, okay. Now, okay, it's clean enough. I'll go ahead and do that right now. X minus y plus z equals 2. I'm good. The sum of the first 2 numbers minus the third equals 0. Okay, it looks like all these are clean. They start you off with easy enough problems. The sum of the first 2 minus the third equals 0. So there's my system of 3 equations. What's very nice is there are 0 coefficients. So when I do elimination in any set, I'm good to go. I don't have to multiply by anything to continue. Okay, the best ones to eliminate by are y or z. And the reason is because I can pair z in the second and third equation and the first and second equation and eliminate z minus z, z minus z. Or I can eliminate y in the first and second equation and the second and third equation to eliminate my y's. So what do we choose? I will go ahead and choose eliminate z, just so I have x and y together. Okay. So let's eliminate z first. I want to add the first and third equation together, because that'll be z minus z. So x plus x, I'll get 2x plus 2y equals 6. Okay, that's first and third equation. Now I'll add the second and third equation here to get z minus z is 0. Okay, so here I'll get 2x. Now check this out. Negative y and positive y, those eliminate too. I'm in good shape. 2x equals 2. Well, not 2x. 2x does equal 2x, but 2x equals 2. So here's my system. That's funny. Sometimes people here, they go, wait, what do I do next? I can't do whatever. You can do elimination if you want, but this is kind of a substitution thing here. I want to use substitution. 2x equals 2. Let's solve for x right here. X equals 1. I'm already good to go. Substitute 1 into this equation here. 2 times 1. 2 plus 2y equals 6. Subtract 2. 2y equals 4. And y equals 2. Hey, This is going to be 1, 2, and 3. I didn't even know that. Anyway, you choose any equation for z. Let's just choose the top one. Let's do it. 1 plus 2 plus z, that rhymes with 3. 3 plus z equals 6, and z equals 3. Take a look at that. That's another order triple. We get 1, 2, and 3. What are the odds? Honestly, I didn't know that. This is my first time doing this. Okay, so we got 1, 2, and 3 as our answer. We found the numbers. That's the important part here. Answer the question that's asked. Because what's important? They might not ask you to solve for your variables you define. They might say, what is the sum? Well, not obviously what is the sum, but what is the second number, right? You want to answer what they ask. Important. Okay, number 5. In a triangle CPR, so I'm just going to draw that. If you remember geometry, there we go. The measure of angle P, that one, is 10 less than twice the measure of angle C. All right, so I'm going to use it says find the angle measures. We know that these are measured as angle C. C is measure of angle C, that's in degrees. P is measure of angle P in degrees. I should say measure of. And R, notice I'm using lowercase letters, measure of angle R in degrees. Okay, those are the variables defined. The triangle CPR, all right, here we go. The measure of angle P, so P, the variable, is 10 less than, again, what that means is on this side I'm going to subtract 10 from whatever I have. Because P is 10 less than, you have to subtract 10 from that to match P. 10 less than twice the measure of angle C. So P equals 2C minus 10. I'm not going to yet write that into a form because I don't yet know where R fits in this whole thing. The measure, what is angle B? This must be a P. The measure of angle R is 10 more than 6 times the measure of angle, I'm guessing that's P. Find the angle measures. Okay, now, we have 2 equations. We need a third. They didn't tell you any more information. Where will we find that? Do not forget that this is a triangle. And in a triangle, if you know the angle sum theorem, all 3 of these guys have to add up to 180 degrees. Okay? So if that's the case, now look, we already have some things that we can do substitution with. I might want to do that, right? That might be to my advantage to use substitution. For the sake of practice, maybe I will use substitution for this one. But I will line up these variables. I will recreate these so that I have equations. In case I wanted to use elimination, there might be a chance that I do. In which case, I'll subtract 2c here. You know what? In fact, I'm going to subtract p and add 10. So I'll get 2c minus p. Now I'm going to skip that r because there's no r in this equation here. Equals positive 10. And here, we can get, let's see, minus 6p. Minus 6p. You know what? I'm going to actually subtract r and subtract 10. We'll get 6p minus r equals, what did I say, subtract r, subtract 10? Negative 10. The main reason I'm doing that, look, it's important to make things easier for you. The reason this makes this easier for me is I know if I want to use elimination, I can do that immediately. I can add r and negative r without having to multiply by negative 1 later. And I can add p and negative p without having to multiply by negative 1 later. Okay. Actually, again, for the sake of time, I will go ahead and go straight into elimination. Now, the main reason is because I want you to see a strategy that I can use for elimination. I have one equation that's missing r, and I have one equation that's missing c. So what you can actually do here is I can take one of these equations right now and say this is one of my 2 equations, like this one, 2c minus p equals 10. This can already act as one of my 2 equations with 2 unknowns, right? You have to whittle it down to 2 equations with 2 unknowns. I already have one. There's no need to pick 2 different pairs and eliminate when I can already eliminate r. Now here, I take a look at these r's. I should probably eliminate these r's right here. So which means I should add the first and third equation, because then I'll have an equation that only has c and p, which is what I want here. So if I add, I'll get c plus 0, which is c. So c, p plus 6p is 7p, equals 180 minus 10, which is 170. So I have now created a system, 2 equations and 2 unknowns, and I didn't need to do elimination twice. I only needed to do it once. Okay. Now again, could have I done some stuff here with substitution? Yeah, probably would have taken more time though. All right, elimination. Now we haven't run into this yet in these problems where I had to multiply by a negative number, at least not that I recall. I want to eliminate something here. You know what? In fact, here let's just do substitution this time. Let's have some fun. I'll solve for p right here. I'll subtract 2c. So negative p is negative 2c plus 10. So p is 2c minus 10. If that's the case, I'll plug in 2c minus 10 in over here for p. So I'll get c plus 7 times 2c minus 10 equals 170, which is c plus 14c minus 70 equals 170. Add 70 to both sides. You see why elimination sometimes becomes a hassle. I see how the preferred preference is normally elimination. 15c equals 240. Ooh, 240. How do you divide that by 15? C, 150 plus 90, I'll get 16. So C is 16. Remember, this is an angle measure. My angle measure of C, 16. Okay. Okay, what do I do now? Let's plug in 16 in for C right there. So P will be 2 times 16 minus 10. P is 32 minus 10, which is 22 degrees right there. And finally, R, you have to use any sort of equation right here as we go along here. R will be, let's go and use this one, right? We already solved for P. Might as well just plug that in. 6p minus, 6p minus r is negative 10. Okay, plug in 22 for p. 6 times 22 minus r equals negative 10. That is, wow, 132 minus r equals negative 10. Subtract, negative r equals negative 142, and r is 142. Okay, so your final answers are, again, if you want to write this as complete sentences or whatever, measure of angle C, I believe, was 16 degrees. Measure of angle P was 22 degrees. And measure of angle R was 142. Now, you might take a look at it and say, does that make sense? Now, remember, this is the first time I'm doing this. Did I do it right? I sure hope so. One way I can double check is say, okay, in a triangle, these should add up to 180. 22 plus 142 is 164. 164 plus 16 is 180. I feel like I'm right. Am I for sure? I don't know. You have to double check all 3 equations if you really want to do that. Or do the problem all over again. But yeah, you double check that and you say, okay, does it make some sense? A little bit. Maybe read the problem again. It says the measure of angle R is 10 more than 6 times the measure of angle P. So R is going to be significantly bigger than P. I'm expecting that. Okay, so I'm kind of expecting that answer there. So that's my final answer there. I hope that was good. Okay, I got 2 more problems for you. Now, these are on a different worksheet. These were on a class worksheet that had 8 different problems, the last 2 of which I did not actually go over in class. So I want to go over these ones now for those people. So that's why there's a star there. Go and find that worksheet. I do forget what it's called. In the triangle at the right, angle A is 8 times the size of angle B, and angle C is 3 times the size of angle B. What is the measure of each of the angles? Okay, this one's actually it's actually kind of straightforward. I feel like this one's a little easier than the other problem you just did. So one thing I'm going to talk about, first of all, A is measure of angle A in degrees. They're asking for those. B is measure of angle B, and of course, coup de grace, C is measure of angle C. Why not? Okay, one thing we know, I'm going to set up this part of my equation immediately. A plus B plus C equals 180. We're talking about triangles. We know degrees plus angles of a triangle add to 180. Bonus points if you know why that's true. Okay, size of angle A Angle A is 8 times the size of angle B. Now that does not mean you multiply 8 times 8. A is 8 times angle B, meaning you have to take angle B and multiply by 8 to match A. So A equals 8B. So if I wanted to, I'm going to keep this here, but if I wanted to write this in my system, I'd subtract 8B, and I'd get A minus 8B equals 0. C is 3 times the size of angle B. Same idea. Multiply B, triple B, you get C. So if I'll subtract C here, I'll get 3B minus C equals 0. Kind of interesting problem, but again, you're looking at something where you have two different, I mean, you only need one, but you have two different equations where you can play around and say, I only need to eliminate one variable. So you want to take a look and say, all right, C is missing in this one, and if I add straight down, I can eliminate C. This is almost identical to the previous problem in that I'm picking the middle equation to choose as one of my two equations with two unknowns, A minus 8B equals 0. And I'm going to add down these guys right here, and when I do it, I eliminate C, so I'll have another equation where I only have A and B. So let's do that. I'll do first and third equation. A plus nothing is A. B plus 3B is 4B. And that equals 180 plus 0, which is 180. Okay, so I have two choices here. I can either multiply one of these by negative 1 to eliminate A, or I can multiply the bottom by 2 to eliminate B. And I don't want to multiply by 2. Yeah, let's multiply by 2. Multiply the bottom by 2, and I'll get 2A plus 8B equals 360. And I add down here. Notice I'm eliminating my B's here. Let's get rid of that for a second. 2A plus A is 3A. 8B minus 8B is 0. So I get 3A equals 360. Divide by 3, I get A equals 120. So one of my angle measures is 120 degrees. And that seemed like the largest one anyway, because it was 8 times the amount of B. Okay, what do I do now? Substitute 120 into somewhere. Anywhere. It looks like I want to substitute it into here. Let's do it right here. 120 minus 8B equals 0. 8B equals 120. And that would be B equals, I think that's 15. 15 degrees there for B. Okay. Now you can substitute A and B back in one of these equations and solve for C. But if you remember, C, oh, you know what? In fact, I could have done this right here as well for B. C is triple the amount of B. So really C is just 3 times 15, which is 45 degrees. So again, just going through the work, your own process is your own thing. Here, measure of angle A is 120 degrees. Measure of angle B is 15 degrees. And measure of angle C is 45 degrees. Those are your final answers. Yes, those add up to 180 degrees. I feel like I'm on the right track with that. We're good to go. So again, you're answering the question that's asked. What is the measure of each of the angles? Okay, final one before the bonus extra credit problem, which I haven't looked at, really. I know it's 4 equations and 4 unknowns, so I'm kind of scared. In January, February, and March of last year, the overall average temperature was 65 degrees outside. That was my typing. My bad. That means outside. The average temperature in January was 3 degrees less than the average in February. In March, the average temperature was 6/5. Ooh, a fraction. The average temperature in January. What was the average temperature in each of the months? It looks like we've been very consistent in initializing them by their first letter. So January, so J doesn't equal January. I know people write that a lot, and I know what you're doing when you use that, but I want you to keep a conscious effort of what you're talking about. You are using variables to relate to what you don't know, and what we don't know are the average temperatures per month. So this is average January temperature, and that's in degrees. Again, we've been doing a lot of degrees here. Different kinds of degrees, sort of. F, average February temperature, also in degrees, and M for March. I really don't like my handwriting here. I wish it was better for y'all. Alright, let's go different color here. Let's look at the information. January, February, and March of last year, overall average temperature was 65 degrees. So they say average temperature in 65. So here's an important thing. This isn't just adding. They do say overall, but I'm not just adding these guys to get 65. No, no, no. I am taking these and taking the average of them. And the average means add them all up and divide by the number of values there are. So if I'm going to write this in my official system, I don't want a fraction. You know that. Multiply both sides by 3. And we get j plus f plus m equals 65 times 3, which is 195. So that's one equation. Second equation, the average temperature in January. Now, they say average again, but they don't mean average like, they mean average in terms of days. You don't divide January by 3. It's January divided by 1. It's just J, right? We called that average temperature. The average temperature in January was 3 degrees less. So J was 3 degrees less than the average in February. So if the average in February is 70, the average in January is 67. Subtract 3. So there's another equation. I'm going to go ahead and subtract f. So I'll get j minus f equals negative 3. There's a second equation. Okay. In March, the average temperature was 6/5 the average temperature in January. So if I take the average temperature in January and multiply that by 6 over 5, take 6/5 of it, I will get the average temperature in March. Okay. Now, as you know, I don't like fractions. I'm going to multiply both sides by 5 here, and I'll get 5m equals 6j. And if I want to write this in terms of these equations over here and create my system fully, I'm going to, let's go ahead and subtract 5m. I'll get 6j. Whoops. Let's make that black. I'll get 6j minus 5m equals 0, actually. Okay, once again, you're in this situation here. I have a system, and I'm missing variables in these, and that's a good sign. So you can do one of two things. You can either, one, say, I want to take the middle equation and use that as one of my equations and eliminate m for the other one. Decide if you want to do that now, because what I'm going to do is say, that means to eliminate m, I have to multiply the top by 5 if I want to use elimination, obviously. And then I have to do 195 times 5, and I don't really like that. What I do see, however, is I have another equation with 2, and say, okay, I can use that as 1 as long as I eliminate f in these two. Oh, look, I just have to add down and I can eliminate f. So I'm going to go ahead and do that. So one equation I have is 6j. That's kind of thick. One equation I have is 6j minus 5m equals 0. The other equation, if I write down the line, I'll eliminate f, and I get 2j plus m equals 195 minus 3. That's 192. Okay, now I have a system of two equations and two unknowns. Let's go ahead and do, I don't want to go back and do substitution there, and I don't want to do it here because either I end up with a fraction or a big number to distribute. So let's go ahead and eliminate. Let's multiply the bottom. It looks like I got to multiply the bottom either by 5 or by negative 3. And it looks like I still have to multiply by 192 anyway. Let's go to multiply the bottom by negative 3. Practice that negative stuff. Okay? We'll get, instead of that 6, so we got 6j minus 5m equals 0. Multiplied by negative 3, I get negative 6j minus 3m equals negative, give me a second there, negative 276, negative 576. I apologize if I'm wrong, but I'm sure the math will speak for itself here. And eliminate. We get negative 8m equals negative 576. Negative 576. Divide by 8. I actually don't know this. Let's do some work here. 800, 400, 80, 60. So that would be 50, 60, 72. M equals 72. Is that right? Should I try that? Yeah, 576. Perfect. All right, M is 72. What did M represent? Average temperature in March. Now, as you do this problem, I want you to assume we're probably talking about Northern California here. March average temperature should probably be warmer than February and January. So when you answer this question, say, am I on the right track? Well, 72 is more than the average we were talking about anyway, which was 65. I think I'm on the right track with my answers. These should make sense. When they create these problems, they have a little bit of logic applied to them. One would hope. And if they don't, you know what? Make sure your math is right. Okay, I'm going to plug in 72 for M. I'm going to go and do it here. Go 6J minus 5 times 72 equals 0. 6J minus, that is negative 360 equals 0. 6J equals 360, so J is 60. That's 60 degrees in January. Okay? So, got to figure out February. We got 60 for January, 72 for March. Let's go ahead. J plus F plus M is 195. So, J plus F plus M equals 195. So that's F plus 132 equals 195. And check that out. Look, F is 63 degrees. Not much warmer than January, just a little bit. It has shorter days. Maybe we didn't get to account for as much. But if I were to type this out in a sentence, because I haven't really practiced that with you yet, at least not on this chapter review, I'd say January had an average temperature of 60 degrees. Apparently I can't type. It's actually dark in here. February, etc., had an average blah, blah, blah. 63, and March, 72. Okay. Remember, you answer the question, right? Don't forget to answer the question. I don't know if you have to write in a sentence every single time, but answering it in a sentence makes sure that you understood that you answered the question that was being asked. Okay, so that's it as far as that stuff. The last thing is an extra credit problem, and it's a challenge problem. It's to see how much you know and all that stuff. So let's see what we got here. Because what we're going to have to do, if you remember what we did for systems of 3, because the stuff will still make sense. The process, whoops, that's word problems. The process will still make sense. We have to get a goal. Get a system of 2 equations with 2 variables. Now our goal is going to get a system of 3 equations with 3 variables, so then we can get into a system of 2 equations with 2 variables. So this is going to be a little bit of fun. I hope they set it up well enough, because, you know, to be honest, I'm kind of nervous how long this is going to take. Hopefully they set this up enough so that I know what to eliminate. I need to eliminate one variable out of all of these, and you have to make that choice very quickly. So my choice, I do not want to eliminate W, because I feel like, first of all, I'd either have to divide by 2 to get down to W, or multiply by a set of numbers to get there, and they're all positive. Bad choice there. I'm thinking maybe do Y, because I have to eliminate these in any sort of senses I add, and I don't have to do much multiplication except for here. I have to multiply one of these by 2. Okay? So pick any pairs of equations here to multiply, to add and eliminate Y. That'll be my first choice. So I'm going to add 1 and 2 to eliminate Y. So when I do, I'll get 3W. And look, X gets eliminated in the process too, which is kind of nice. 3W, but I'm going to leave some room. I'll get plus 3Z equals 9. And by the way, this will be my unofficial system actually, because I want to divide by 3 already. This is actually coming out pretty good so far. I'm feeling kind of happy. So W plus Z equals 3 if I divide by 3 there. Okay. To eliminate another set of Y's, let's go ahead and multiply these guys by 2 if I want to eliminate this, if I want to combine these red guys right here, second and third equation. So if I multiply by 2, I'm going to get 4W minus 2X minus 2Y plus 2Z equals 14. And I add that with 2W plus 3X plus 2Y minus 2Z, or I'm sorry, not minus 2Z, minus Z. I got ahead of myself there. One thing, the problem about these problems is you just don't want to screw up. You really don't want to screw up, because then because then you're done. You know, you say where did I screw up, and it's hard to debug. It's hard to look back and say, what did I do wrong? It really is. So here's my equation here. So let's go and rewrite that here. 6w plus x plus z equals 12. I'm on my good path to get to where I need to. It's going to kind of be a system of 3 equations and 3 unknowns again. Okay, eliminate y. I'm just going to add it with the first equation. There's nothing that says you have to multiply this by 2 and add with this one. Just because I did first and second, second and third, doesn't mean I have to do third and fourth here. I'm going to go ahead and do, in purple, the first and the last one because I have plus y minus y. So adding straight down, mental math here, we get 4w plus x minus 2x, that'll be minus x. Looks like this is kind of clean. It's nice. 0y minus 2z equals 2 minus 2, which is 0. Okay, I have a system of 3 equations, 3 unknowns. We've done a lot of this before, and check this out. We have one of these situations again where I can add where I can get a system of 2 equations, 2 unknowns right off the bat because I have one of them now. And look, my x, if I add these x's here, they will eliminate immediately. I bet they set this problem up for us to do this exact thing. Again, this is my first time trying it. I'm lucking out, so it seems. I'm going to add the bottom 2 here, and I'm going to get 6w plus 4w is 10w. X plus negative x is 0. Z minus 2z is negative z equals 12. I really like elimination more than substitution. I wanted to defend substitution a little bit. I just, in all good faith, can't. Here's where I suddenly don't like my problem. I've eliminated, and I got 11w equals 15. I really hope I didn't screw up somewhere, because suddenly I have a fraction. I'm going to pause this for a moment and see if there's anything that I can change. Okay, I unpaused us. Screwed up a little bit. It's not going to be that big of a deal here, but I multiplied by 2 here, and I didn't multiply by 2 here. So this should be 4z, in which case I get 3z. Okay? I'm sorry, 3z. And when that's 3z, that was right here, so that's 3z right there. So looking back, and again, you know, it's a small thing. I didn't really have to do too much there. I can still eliminate x there. So this will be, as I eliminated x, that'll be plus z instead of minus z. So I'm looking back, hey, you know what? We all screw up. I'll make careless mistakes. It really is happening because I'm talking through it with you. So I can still eliminate z. I just have to multiply one of my values by negative 1. And I'm going to multiply the top by negative 1 because I want to get positive numbers. I like positive numbers more. So think about this. This is negative w minus z equals negative 3. So it's kind of subtracting. So we get 9w, this is 0, equals 9. That looks a lot better. W equals 1. Excuse me, 1. You feel like if you get a fraction answer, you might have done something wrong. So you really do want to double check that. And it only took me a minute to look. Okay, w equals 1. Now, plug it into equation. You can plug any equation that we've set up here that has any equal sign and any w, especially if the balance is correct. But I have one right here that'll do best for me. W plus z equals 3. 1 plus z equals 3. So z equals 2. So I plugged in this right here into there for that equation. Okay, w is 1, z is 2. We're getting there. Find an equation with w and z if you want. Here are a couple. I'll use the positive ones here. 6 times 1 plus x. Notice we're going to solve for x plus 3 times 2, which is z, equals 12. 6 plus x plus 6 equals 12. 12. X plus 12 equals 12. And x equals 0. Subtract. So 0, 1, and 2 for x. So let's see. 1 for w, 0 for x, 2 for y, 2 for z. We're going to solve for y. I'm going to use my original equation, just have to add straight across. So w plus x plus y plus z. W plus x plus y plus z equals 2. 1 plus 0 plus 2 says y plus 3 equals 2. Y equals negative 1. There's nothing that says you can't have a negative answer. So my final solution is 0, comma, negative 1, comma. I'm sorry, w's first. So w is 1, w, x, y, z. You can double check that. Again, I'm saying you can because I'm not gonna. I trust those answers. They're small, they're clean, not fractions. They probably work out. And you know what? That wouldn't take too long to do. But there's your extra credit there. And thanks for bearing with me when I made my mistake. So there's all my work. I really hope that that worked out for you. And good luck the rest of the way on your test. If you have any other questions, please let me know. Super glad to help.